Welcome, curious minds, to another deep dive. Today, we're plunging into a part of the AI world that often stays in the shadows. What happens after an AI model is trained?
Right.
You might think the big costs and complexities lie in teaching these massive AI models, in that initial training phase.
That's the common assumption. Yeah.
But what if I told you that our sources reveal a surprising truth about where the real financial and engineering challenges often lie?
Hmm.
Today, we're challenging a fundamental assumption about AI costs, revealing where the real game is played, the crucial phase of inference.
That's where the AI actually does something.
Exactly, where it comes to life, making predictions in the real world. Our mission is to pull back the curtain on this often overlooked aspect, explore the cutting-edge hardware and cloud platforms making it possible, and help you understand the critical trade-offs involved in deploying AI at scale.
And there are definitely trade-offs.
We've got a fantastic stack of sources for this one, and we're ready to unpack it.
Let's do it.
So let's dig into the specifics here. Our sources highlight that an AI model's lifecycle really has two distinct vital phases: training and inference. Training is where the model learns from vast amounts of data, much like a student studying for an exam.
Right, absorbing all that information.
Inference, on the other hand, is its practical application, the moment it takes that knowledge and applies it to make real-time predictions on new, unseen data, like the student applying what they learned to solve a problem in the real world.
And what's truly eye-opening here, I think, is the sheer economic reality. While training gets a lot of attention and investment, and often feels like the biggest hurdle.
It does, yeah. The big compute bills everyone talks about.
Exactly. But our sources consistently point out that inference can account for up to 90% of the total machine learning costs over a model's lifetime.
90%. That's huge.
It really is. Think about it this way. Training is often a one-time or periodic capital expenditure. You build the factory. But inference is a continuous operational expenditure, incurred with every single user query, every prediction the model makes. That's like the electricity bill for keeping the factory running 24/7.
Ah, okay. That makes sense.
And this fundamental difference drastically shifts the engineering priority from just building a model to efficiently running it at scale.
That's a massive shift in perspective, isn't it? As someone navigating this space, you might have initially focused completely on that training bill,
Right.
but our sources really force us, and you listening, to rethink where the real long-term economic leverage lies. So if inference is such a continuous cost, how do we even begin to quantify its performance and efficiency?
Good question. To quantify this critical phase, we primarily use two metrics: latency and throughput.
Okay, latency and throughput.
Latency is the time it takes for a single prediction, essentially, how fast the AI responds to one request. This is crucial for real-time applications where, like, every millisecond counts.
Like autonomous driving or maybe a live video feed?
Exactly. Or instant chatbot responses. Throughput, on the other hand, is the number of inferences a system can handle per second. Think of it as the sheer volume it can process.
So more like batch processing.
Yeah, or high-volume services like automatically tagging thousands of photos or processing millions of financial transactions. Optimizing these isn't just about technical finesse. It directly impacts user experience, scalability, and ultimately your operational costs.
Got it. It's clear these metrics are kind of the heartbeat of deployed AI. Now, as AI models themselves grew exponentially more complex,
Which they did rapidly.
the hardware processing them had to evolve just as quickly. Inference started on general-purpose CPUs, right? Then
Yeah.
quickly moved to GPUs because of their incredible parallel processing power.
Which was perfect for neural networks at the time.
But even GPUs, originally designed for graphics, it eventually started to hit some limitations when it came to AI inference specifically.
And that brings up a critical point. If GPUs were so good, why did the industry need to invent something new, something more specialized?
Right. What was the bottleneck?
Well, the continuous and escalating demand for large-scale inference exposed their cost and, maybe more importantly, their power efficiency limitations for this specific type of workload.
Ah, the power draw.
Exactly. While great all-rounders, they weren't perfect for AI inference. This catalyzed the development of custom-designed application-specific integrated circuits, or ASICs, purpose-built for AI.
A6, okay.
Examples like AWS Inferentia and Intel's Habana Gaudi were born from this need. These chips are like specialized engines designed only to perform the calculations crucial for deep learning.
So really focus.
Very focused, delivering superior performance per watt and significantly lower cost per inference by focusing solely on those neural network operations.
What I found particularly eye-opening in the sources was just how intertwined the hardware and software become here. These ASICs aren't standalone magic boxes, are they?
Not at all. They're part of a deep hardware-software co-design ecosystem. They rely heavily on dedicated software development kits, or SDKs, to truly unlock their full potential.
It's like having a high-performance race car. You need the right fuel and the right mechanics, the right software to get the most out of it.
Precisely. The SDK is key.
Now, with that foundation of ASICs and SDKs, let's get specific. What are the champions in this new hardware arena? Let's dive into two prominent ASIC examples. First, AWS Inferentia. What's its secret sauce beyond just being a custom chip?
Okay, AWS Inferentia, it's Amazon's custom chip, built around what they call Neuron cores.
Neuron cores.
Yeah, these aren't your typical CPU cores. Imagine them as miniature, hyper-focused arithmetic units designed specifically for matrix multiplications and convolutions.
The mass behind neural nets.
Exactly, the bread and butter of neural networks. This focused design allows them to crunch numbers with incredible efficiency and low power consumption that general-purpose GPUs simply can't match for this specific type of work.
And how do developers actually use it?
They interact with it using the AWS Neuron SDK. For PyTorch developers, the core step is a function called torch_neurons.trace. Think of it like hitting a turbo compile button for your PyTorch model.
Okay.
It translates the model into a highly optimized format that speaks the Inferentia chip's native language, unlocking its full potential without needing you to rewrite your model from scratch.
And the benefits?
Its primary advantages are cost efficiency. Our sources show it can be up to 70% lower cost per inference than equivalent GPUs, and high performance, with mixed precision support too.
70% lower cost per inference is massive, but does that come with a trade-off? Like, in terms of flexibility or the sheer learning curve for developers used to say NVIDIA's ecosystem, what do our sources say about that friction?
That's a great question, and it's a common concern when moving to specialized hardware. I mean, there's always some learning curve with a new SDK, right?
Sure.
But the AWS Neuron SDK aims to minimize this by providing familiar interfaces for popular frameworks like PyTorch. The friction is often less about rewriting your core model logic and more about understanding the compilation and deployment pipeline specific to the Inferentia architecture.
So it's more process than code?
Largely, yes. It's a strategic trade-off. A steeper initial learning curve potentially yields significant long-term cost savings.
Okay, makes sense. And then we have Intel Habana Gaudi. How does it compare in this specialized landscape?
Intel's Habana Gaudi accelerators are interesting because they're designed for both training and inference.
Dual purpose.
Right. Developers also use a dedicated SDK, the Habana SynapseAI SDK. Intel aims for ease of migration from GPU code here, often just requiring a change to specify Habana processing unit as the target device in PyTorch.
So potentially less friction there.
Potentially. It supports both eager mode and lazy mode. Eager mode is like executing each instruction one by one immediately, great for debugging, simpler models, getting immediate feedback. Lazy mode, on the other hand, is like writing down a full shopping list before going to the store. It plans out all the operations ahead of time, then executes them in one optimized go.
More efficient, but maybe more complex.
Exactly. It often requires a specific signal, like htcore.mark step, to trigger the execution. This flexibility helps optimize for different workload needs, particularly complex ones, where planning all operations together can yield big efficiency gains.
The flexibility sounds great, but I imagine getting lazy mode right with that htcore.mark step queue might require a deeper understanding of the model's computation graph. Is that a common hurdle for developers migrating from GPUs?
Absolutely. While it's powerful for optimization, lazy mode does require developers to be more aware of their model's computational flow and explicitly manage when operations are compiled and executed. It's definitely a different mental model than the more immediate eager mode.
Right.
It can indeed be a hurdle for those accustomed to simpler GPU deployment patterns, but for those pushing the boundaries of performance, that control is invaluable.
So we've talked about these powerful, low-level ASICs, but let's be real. Many of us, many teams, live in the world of managed cloud services, where much of that infrastructure is abstracted away.
Yeah, that's very common.
How do platforms like Azure Machine Learning and Google Cloud Vertex AI streamline AI deployment for the everyday user or team? Let's start with Azure.
Okay, Azure ML. These managed cloud platforms offer a higher level abstraction, basically handling much of the underlying infrastructure management for you. Azure ML primarily uses managed online endpoints for real-time predictions.
Managed online endpoints, got it.
The workflow involves defining an environment, registering your model, and then, crucially, writing a scoring script, usually score.by.
Okay, the scoring script, what does that do?
This isn't just writing any code. It's about adhering to a specific architectural pattern that tells the Azure platform how to efficiently run your model. This script has two essential functions: a init, which is called just once when the endpoint starts up.
Like a setup function?
Exactly. To load the model into memory, imagine setting up your workstation before you start work. And then run raw data, which is called for every incoming inference request. This is where the actual prediction happens for each new piece of data.
Ah, so init once, run many times.
Precisely. This separation ensures efficiency, as the model only needs to be loaded once, not for every single request.
Makes sense. And Google Cloud's Vertex AI, how does it approach this?
Vertex AI also offers online prediction via endpoints. Much like Azure, developers can either use pre-built containers for standard frameworks, which are super convenient.
The easy button?
Kind of, yeah. But for maximum flexibility, especially if your model has unusual dependencies or needs custom server logic, you can provide custom Docker containers.
Docker containers. Okay, more control there.
Immense control. This is incredibly powerful because it gives you complete control over your environment. However, if you go this route, your container needs to be set up like a tiny web server.
Right, it has to respond to requests.
It must run an HTTP server on port 8080 and have specific digital doorways endpoints, one for checking if it's healthy and ready, and another for sending it new data to predict on a predict.
So the platform knows how to talk to it.
Exactly. You then push this container to Google's artifact registry. It offers immense control, but naturally requires more DevOps expertise. Building and managing containers isn't trivial.
That's a powerful dilemma, isn't it? On one hand, you've got the raw power and potential cost efficiency from these custom ASICs, and on the other, the ease of use and abstraction from managed cloud platforms. How do you navigate that choice? What are the critical trade-offs that leap out to you from the sources?
This is really the central question for many teams, and our sources highlight it as a balance between, well, cost efficiency, raw performance, and perhaps most importantly, developer experience and MLOps integration. Specialized ASICs like Inferentia and Gaudi typically offer the lowest cost per inference and highest raw performance. They're like owning that custom-built race car incredibly fast, but they demand a steeper learning curve and expertise with their specific SDKs. You have more control, but also more responsibility.
Higher barrier to entry, potentially.
Definitely. Managed cloud AI platforms, while potentially having a slightly higher cost per inference, but not always provide much higher level abstraction, they're more like getting a high-performance rental car.
Okay.
It might not be quite as fast as a custom build in every single scenario, but it comes with a fully managed MLOps experience, simplifying deployment, management, monitoring, and scaling.
So the choice really boils down to?
It ultimately depends on your workload's cost sensitivity, your precise performance needs, like do you really need those extra milliseconds of latency reduction, and your team's operational priorities and existing expertise.
To really connect these dots and see these trade-offs in action, our sources detail a fantastic capstone project. It involved deploying a state-of-the-art YOLO-8 object detection model,
A popular model.
as a real-time API endpoint across all these different options we've discussed. AWS Inferentia, Azure ML using GPUs, GCP Vertex AI also on GPUs, and Intel Habana Gaudi.
A direct comparison.
Exactly. Then they subjected each one to a rigorous load test using Logist, which is a Python-based performance testing tool to simulate real-world traffic.
Yeah, Locus is great for that. The results from such a benchmark are incredibly insightful, directly translating our discussion into tangible numbers.
So what did they find?
For this specific object detection task, the illustrative data, and remember, results can vary, showed AWS Inferentia demonstrated impressive high throughput, around 150 requests per second, or RPS.
Okay, 150 RPS.
With remarkably low average latency at just 65 milliseconds and a very competitive estimated cost of about 1.40 cents per million inferences. It really shone on cost efficiency in this test.
Wow, that's compelling. What about the managed platforms?
Azure ML GPU and GCP Vertex AI GPU offered slightly lower throughput, somewhere in the 85 to 90 RPS range, and higher latency, around 108 to 115 milliseconds. Their estimated costs came in around $1.72 to 1.857 per million inferences.
Still pretty good, but definitely higher cost and latency than Inferentia in this case.
Right. Still strong contenders,
Mm.
especially when you factor in their managed benefits and maybe broader GPU availability or familiarity.
And Habana Gaudi?
Habana Gaudi, while having strong raw performance, 135 RPS and 72 milliseconds latency, so faster than the GPUs.
Better latency than the GPUs, yeah.
It actually showed a higher estimated cost of approximately 3.37 per million inferences in this particular configuration and pricing model used for the text.
Oh, interesting. So performance isn't everything for cost.
Exactly. This highlights a crucial point. Raw performance doesn't always directly equate to the best cost efficiency. The specific workload, the pricing of the instances, and the configuration can significantly influence the economic outcome.
This comparative analysis truly brings everything into focus. It shows that for this specific object detection workload, AWS Inferentia can indeed offer the best cost efficiency.
In this scenario, yes.
But it also underscores that the managed platforms like Azure ML and Vertex AI offer that significant advantage of streamlined MLOps workflows,
That could be huge.
which can be invaluable for teams prioritizing ease of deployment and ongoing management over, squeezing out every last drop of raw, granular cost optimization.
It's about finding the right balance for your needs.
Wow, what a deep dive into the practical realities of AI deployment. We move from that surprising truth about AI inference costs
The 90% figure, yeah.
to the nitty-gritty of specialized hardware like Inferentia and Gaudi, managed cloud platforms, SDKs, scoring scripts, Docker containers, and even looked at real-world benchmarks to see how these choices play out.
It's a complex landscape.
It really is. It's truly remarkable how deep the rabbit hole goes once you move past training and into the world of efficiently delivering AI.
And if we connect this to the bigger picture, it profoundly underscores that the future of AI isn't just about building better, smarter models. It's equally, maybe even more, about efficiently and economically delivering those models to users at scale.
Right. The best model is useless if no one can access it affordably.
Precisely. The fundamental choices in hardware and deployment strategies directly impact the real-world accessibility, the responsiveness, and the economic viability of almost every AI application we interact with.
So what does this all mean for you listening? As AI continues to evolve at lightning speed and as specialized hardware becomes increasingly common, how might the skills required for deploying and managing AI models continue to shift?
That's a great question. Will we see an even greater specialization in roles like inference optimization engineer?
Or perhaps a convergence where DevOps and ML skills become even more tightly integrated?
It's hard to say for sure, but change is definitely coming.
We encourage you to consider this question and keep exploring the incredible innovations happening in this fascinating space. Thank you for joining us on this deep dive.
Yeah, thanks for tuning in.
We look forward to our next exploration together.